evening, everyone. Welcome to our presentation on approximation algorithms for scheduling time-critical jobs on multi-processor systems. This work is authored by Sudarshan K. Hall, and I, along with my teammates, will guide you through our findings. Today, I'll introduce the motivation behind the research, discuss key scheduling problems, review various algorithms, and focus in detail on our approximation methods. So let's begin by setting the stage with some groundwork and motivation. Scheduling plays a crucial role in any system where timing is critical, especially in real-time and control applications. In these systems, missing a deadline can lead to system failures or degraded performance, while multiprocessor systems offer the advantage of higher overall performance. They also introduce added complexity, managing job assignments. Our goal here is to develop an efficient approximation algorithm that ensure all jobs meet their deadlines without overburdening the processor in a complex multiprocessor environment. In a problem domain, we'll focus on periodic time-critical jobs. These jobs arrive at a fixed interval and must be completed before the next instance arrives. They're independent, which simplifies some aspects but also means you can't rely on inter-job dependencies to optimize scheduling. Each job is represented of J is equal to C comma P, where C is the processing time and P is the period. The key metric is the utilization factor, which is P by P, which indicates the fraction of per processor's capacity that each job requires. This factor is essential in, in trying to find out how many jobs can be handled by a single processor without exceeding its capacity. Scheduling algorithms come in several types. In hard real-time scheduling, missing a deadline is not an option because it can lead to catastrophic system failures. On the other hand, soft real-time scheduling allows occasional misses, even although they can still reduce overall performance. Furthermore, we differentiate between static scheduling, where the entire schedule is pre-computed and fixed, and dynamic scheduling, which adjusts in real time based on the current stage of a system. Our work primarily targets in dynamic environments where conditions can change rapidly. There are two main approaches to multi-processor scheduling. Global approach allows any job to be processed by any available processor. This maximizes flexibility and resource use, but it can complicate scheduling decisions significantly. In contrast, the partitioning approach assigns jobs to specific processors ahead of time. This method simplifies the scheduling process and ensures a degree of isolation between the processes. However, it may lead to load imbalances, where some processors are overburdened while others are underutilized. Each approach has its merits and challenges, and the choice depends on the application's requirement. Historically, scheduling began with relatively simple algorithms developed in the 1950s, such as Johnson's rule for production scheduling and Smith's rule for single stage processing. However, as systems grew more complex, particularly in the 1970s and 1980s, the researchers began to apply complexity theory to scheduling problems. This led to uh, this led to the realization that many scheduling problems are NP hard, meaning that finding an optimal solution can computationally infeasible as the number of jobs increases. This historical evolution is what ultimately drove the need for efficient approximation algorithms. As the complexity of scheduling problems increased, exact methods like branch and bound became impractical for large systems. This spurred the development of approximation algorithms, which are designed to provide solutions that are near optimal while also being computationally feasible. These algorithms come with performance guarantees, typically measured as a ratio relative to the optimal solution, which makes them highly valuable in real-world multiprocessing environment. This evolution from exact to approximation technique is a cornerstone of modern scheduling research. One of the most challenging aspects of scheduling is its computational complexity. Many scheduling problems are NP hard, which means that the time required to compute an optimal solution can grow exponentially. Sometimes as as bi- as big a big O of 2 raised to n. As the problem size increases, only simplified cases can be solved in polynomial time. This inherent complexity makes it essential to use approximation algorithms that can deliver good solutions in a reasonable time frame, even if they are not perfectly optimal. Approximation algorithms are critical because they allow us to obtain near optimal solutions quickly, which is especially important in real-time systems where missing a deadline can have severe consequences. These algorithms involve a trade-off where we sacrifice a bit of optimality to gain significant improvements in computational efficiency. We often evaluate these algorithms using the worst case performance ratio R of A is equal to NA by N0, where NA represents the number of processes used by our algorithm, and N0 is the optimal number. A lower ratio indicates that algorithm performs close to the best possible solution. Before we move into multiple processors challenges, it's important to review the two foundational processor scheduling algorithms, EDF and RM. EDF dynamically assigns priorities based on the closest deadline and ensures that all jobs are scheduled as long as the total utilization doesn't exceed 1. In contrast, the rate monotonic algorithm assigns fixed priorities based on the length of job periods, and it has been proven optimal for fixed priority scheduling in single processor systems. These algorithms set the stage for understanding more complex multiprocessing scenarios. While PDF and RM work well in single processors, they face significant challenges when applied to multi-processor systems. In a high utilization environment, these traditional algorithms might fail to schedule all tasks, even though a feasible schedule exists, because they aren't designed to handle the complexities of load balancing across multiple processors. This limitation is why centralized approximation algorithms have been developed to effectively manage multi-processor scheduling, ensure that tasks are distributed evenly and deadlines are met. Offline approximation algorithms are designed with the assumption that all job details are available beforehand. The primary objective is to minimize the number of, number of processors needed while still meeting all the job deadlines. There are several notable algorithms in this category, including RMNF, RMFF. FFDU, and RMGT. Each algorithm employs a unique strategy to pack jobs efficiently. Today, I'll focus on two of these methods, RMNF and RMFF, explain the concept, steps, and applications in detail. So, so let's go over RMNF or rate monotonic index fit algorithm. The idea is simple. We sort all jobs in the rate monotonic order, meaning jobs with shorter periods are processed first. Then we pack these jobs sequentially into a processor until adding another job would cause the total utilization to exceed 1. At that point, we move on to the next processor and repeat the process. The strength of RMNF lies in the simplicity and low computational overhead. However, sequential nature can sometimes result in underutilization of available processing capacities. Now let's go over where RMNF algorithm is most effectively applied. Its simplicity and low overhead makes it ideal for systems with limited computational resources, such as embedded systems and IoT devices, where, where low power consumption is critical. RMNF is also well suited for low complexity real-time systems where the job load is predictable and does not vary dramatically. Additionally, it is often used during prototyping and early stage de- design because its straightforward implementation allows for quicker testing and validation of scheduling calls. Finally, we arrive at the RMFF or rate monotonic first fit algorithm, which is the focus of my segment. In RMFF, after sorting the jobs in the rate monotonic order, we assign each job by scanning through the available processors and placing it in the first one where adding the job does not cause the total utilization to exceed 1. This approach typically results in better overall processor utilization than RMNF as it makes more efficient use of available processing capacity. However, the trade-off is that scanning the trade-off is that scanning for a process can take longer, especially as the number of processors increases. Overall, RMFF strikes a good balance between efficiency and resource management. A complex multiprocessors environment. Uh, yeah, Overall, RMFF offers more efficient utilization strategy in complex multiprocessor systems. With that overview complete, I'll now hand over to Abhishek, who will now delve deeper into additional scheduling algorithms and explore the advanced applications. Abhishek, over to you.
I'm thrilled to present today on approximation algorithms for scheduling time critical jobs, focusing on two key algorithms from chapter 32. We'll dive into the first fit decreasing utilization or FFDU and the rate monotonic general task or RMGT algorithms. These are tools for managing tasks where timing is everything, like in aerospace or medical systems. I'm Abhishek, and let's jump in and explore how these algorithms keep critical systems on track. Alright, let's set the foundation. Like, what are periodic time critical jobs or PTC jobs? These are tasks that repeat at fixed intervals and have deadlines that cannot be missed. Think of a heartbeat monitor or a satellite adjustment. The chapter outlines four key traits. They activate periodically, have a constant processing time called C, must finish before their next activation, defined by their period P, and don't depend on other jobs. Each job is a pair C, P, where C by P is the utilization factor, how much fact processor time it demands. Our mission is to schedule these on multiple processors so every deadline is met. Imagine a timeline. A job starts at 0, runs for C units, and must finish by P, then repeats. That's the challenge FFDU and RMGT tackle, and we'll see how they do it under a partitioning approach, locking each job to one processor. Okay, so why do we need algorithms like FFDU and RMGT? The short answer: perfection is too hard. Finding the absolute best schedule for PTC jobs is NP hard computationally. It's a nightmare for job as the job numbers grow. Approximation algorithms step in to save the day. They are not perfect, but they are practical, giving us near optimal solutions fast. We measure them with R, the worst case performance ratio, how many processors they use compared to the minimum possible, or a lower ratio is better. FFDU and RMGT strike a sweet spot. They are efficient enough to use in real systems and good enough to keep deadlines safe. Think of it like packing a suitcase. You might not fit everything perfectly, but you'll get it closed without breaking the zipper. Okay, so let's dive into FFDU algorithm first. The first fit decreasing utilization algorithm. It's an offline method, so it needs all the job details upfront. Here's how it works. Step 1, right? Sort all jobs by their utilization factor C by P from highest to lowest. The hungriest jobs go first. Step 2, take each job and assign it to the first processor where it fits under the rate monotonic or RM scheduling rule. If it doesn't fit, start a new processor. RM is key here. It gives priority to jobs with shorter periods, meaning higher activation rates. It's like packing a moving truck. You put in the big stuff first and find a spot that works, adding more trucks only if you must. This simplicity is FFDU's strength, and it uses RM's predictable priority system to ensure feasibility. We'll see how it performs next, like what's the performance, right? So how does FFDU stack up? Its worst case ratio R is less than or equal to 2. That means in the toughest scenarios, it uses at most twice the processors an optimal solution would. Pretty solid, right? The chapter proves this bound is tight with an example where the ratio gets close to 2. On the speed front, it's a champ. Sorting takes like O of m log m, where m is the number of jobs, and allocation mimics bin packing's first fit, keeping the total complexity at O of m log m. That's fast enough for big jobs sets without breaking a sweat, so FFDU gives a reliable, quick way to schedule, even if it's not always the leanest on processor count. So why pick FFDU? Like, why choose FFDU? It's all about ease and reliability. It's super intuitive. Sorting by utilization is like stacking the heaviest boxes first, a natural approach. It uses RM, which has lower overhead than dynamic priority methods like earliest deadline first, EDF, where priorities shift constantly. FFDU keeps things predictable, which is gold for systems needing stability over max efficiency, like avoiding surprises in critical operations. Plus, being offline, it's perfect when you know your job set ahead of time, letting you pre-plan the schedule. It's not about using the fewest processors, it's about getting the job done and simply on time. So let's look at the FFDU in like real world. Where does FFDU shine in the real world? Think automotive systems like the engine control unit in your car. It handles tasks like fuel injection every few milliseconds or ignition timing. Periodic critical jobs where missing a beat could stall the engine. FFDU partitions these across processors in the ECU, keeping everything humming with minimal hardware. Another spot would be industrial automation. Picture robotic arms on an assembly line, motor control and sensor checks happen on a tight schedule for these. So FFDU assigns them efficiently, ensuring the line doesn't stop. It's about dependable performance in a system where timing is non-negotiable. Cars and factories rely on it daily. So Now let's switch gears. Let's look at the RMGT algorithm, which stands for Rate Monotonic General Task. It's also offline, but it's smaller about resources. So here's the breakdown. First, it splits the jobs into two groups: small jobs with utilization up to 1/3, and large ones above 1/3. So for small jobs, it sorts by a special S value tied to the periods and feasibility, then assigns them using RMST, a tailored RM approach aiming for high utilization up to bounds like natural log of 2 for large jobs. It uses a first fit method without sorting, applying an exact feasibility test for up to 2 jobs per processor. This divide and conquer tactic optimizes how much each processor can handle, making RMGT a step up in efficiency from FFDU. So now let's look at like how does it the performance and complexity look for the RMGT algorithm. So sorry for that. RMGT's performance is a standout. Its R ratio is approximately around 1.75, which is better than FFDU's 2, right? It achieves this with precise feasibility tests from theorem 39.2 and a sharper estimate of the minimum processors needed thanks to lemma 32.6 in the chapter. That means fewer processors in the worst case, a big win, right? But there's a catch. Complexity jumps to O of m square because of those detailed checks and skipping the sort for large jobs. Compared to FFDU's O of m log m, it's slower but more efficient on resources. So RMGT trades speed for a linear processor count, perfect when hardware is at a premium. So let's look at like why do you like choose RMGT? So why go with RMGT? It's about squeezing more out of less. By splitting jobs and fine-tuning assignments, it boosts processor utilization, cutting down the number needed. Think cost savings in hardware or power. It still uses RM for that predictable scheduling we love, but optimizes it closer to what an ideal solution might achieve. It's offline, so it fits the system where you can plan ahead, and it's 1.75 bound, making it a champ in resource tight spots. If FFDU is the quick fix, RMGT is the strategic play, ideal when every processor counts. So now let's look at the RMGT's real world application. So RMGT's real world home is in high stakes systems. Take aerospace like satellite control. Satellites run tasks like altitude adjustments every second, or telemetry pings, saving weight and power, which is everything in space. Or let's consider medical devices, ventilators for instance. Pressure monitoring and alarms must happen on time, every time. RMGT optimizes processors used in a compact battery powered unit, keeping patients safe. It's about efficiency without compromise. NASA and healthcare lean on these kind of smarts, coming from RMGT. So now I'll be moving on to the comparison between these two algorithms, like a head-on-head comparison. So let's put FFDU and RMGT. Performance-wise, the R ratio for FFDU is less than equal to 2. For RMGT, it's 1.75. RMGT wins on efficiency, right? Complexity, FFDU's O of m log m beats RMGT's O of m square. Speed goes to FFDU. Approach, FFDU sorts and fits simply. RMGT divides and conquers with precision. Use case, FFDU is your go-to for quick simple setups. RMGT shines where resources are scarce. Both lean on RM for predictability, but RMGT's sophistication gives it an edge utilization, while FFDU keeps it fast and straightforward, like pick based on your priorities like speeds or savings. Now look at the real world impacts of these algorithms, right? I talked about a few examples. These algorithms like make a real difference. FFDU powers rapid setups like Tesla's real-time car systems or factory floors, keeping production smooth. RMGT drives efficiency in NASA satellites or Philips ventilators, where every processor matters. The chapter notes average performance ratios below 1.5. way better than their worst case bounds. So they are not just theoretical, they deliver. In critical tech where deadlines are like life or death, FFDU and RMGT keep things running reliably and efficiently, impact that you can see every day. uh, I would like to wrap up my presentation. So to wrap up, FFDU and RMGT are stars in scheduling time critical jobs. FFDU brings speed, uh, simplicity and predictability, great for straightforward needs. RMGT offers efficiency and resource savings, perfect for complex constrained systems. Both guaranteed deadlines are met, which is the heart of critical applications, right? As our tech gets more intricate, these algorithms stay essential, balancing practicality and performance to keep systems ticking on time. That's the power of approximations at work. Thank you.
Hello everyone and welcome. My name is Abhishek Alhat and I am excited to present the conclusion of our study on approximation algorithms for scheduling time-critical jobs on multiprocessor systems. This is a fascinating and crucial topic because many industries, including aerospace, telecommunication, and embedded systems, rely on effective scheduling algorithms to ensure critical tasks are executed on time. In this presentation, I will summarize the key takeaways from our study. We will revisit the core challenges, explore why approximation algorithms are used, and discuss important theoretical insights, and compare offline and online scheduling approaches. By the end, we will understand how these algorithms contribute to reliable and efficient scheduling in real-time multiprocessor system. So let's begin. Let me quickly recap the problem at hand. As you know, scheduling a periodic and time critical jobs is a very challenging task. It's NP hard, meaning that finding an optimal solution within a reasonable amount of time is computationally infeasible for large scale problems. These jobs are critical because they have strict deadlines. Missing these deadlines could lead to catastrophic failures, especially in safety critical applications like medical devices, automotive systems, and financial transactions. Multiprocessor systems make the problem even more challenging. Unlike single processor scheduling, where jobs are simply arranged in a queue based on priority. Multiprocessor scheduling requires distributing jobs across multiple processors efficiently while ensuring all deadlines are met. The complexity increases due to factors such as load balancing, interdependencies, and varying job execution times. So, given these challenges, how do we approach finding solutions that are computationally feasible and effective? That brings us to approximation algorithms. In cases where finding the exact optimal solution is impractical, we turn to approximation algorithms. These algorithms don't always guarantee the absolute best solution, but they provide solution within a known bound of optimality. In other words, they ensure that the solution is close enough to the best possible answer within an acceptable margin of error. One major advantage of approximation algorithm is that they strike a balance between computational efficiency and practical feasibility. Instead of spending excessive time computing the perfect schedule, they provide a workable solution that meets performance constraints. Also, for real time systems, predictability is crucial since these systems operate under strict timing requirements. It is essential to have scheduling algorithms that deliver consistent performance. Approximation algorithms help achieve this predictability by ensuring that jobs meet their deadlines reliably, even under worst case conditions. Now that we understand why approximation algorithms are useful, let's look at some of the theoretical foundation that supports these methods. A key concept in scheduling is determining whether a set of jobs can be scheduled feasibly, meaning all deadlines can be met without exceeding available processing power. To access feasibility, we use utilization-based tests. These tests These tests determine whether the total computational demand of all jobs can be accommodated within the available processing time. A useful analogy here is a bin packaging problem, where we try to fit different sized objects which are jobs into a fixed number of bins processors. The goal is to minimize wasted space and pack as efficiently as possible. By developing tighter bonds on processor utilization, we can improve scheduling efficiency, ensuring that we allocate processor time optimally without overloading or underutilizing resources. Let's now examine how these concepts translate into practical scheduling strategies, starting with offline algorithms. Focusing on offline algorithms, those that work when all job information is available in advance. These are particularly valuable in systems where tasks are known beforehand, such as embedded systems or industrial control applications. Starting with rate monotonic next fit RMNF algorithm. This algorithm represents one of the simpler approaches. It first sorts all tasks by their periods, then shorter period gets higher priority. Then it allocates tasks to processor using a next fit strategy. What does this mean is the algorithm places each task on the current processor until it can't fit any more tasks. Then it moves to the next processor. Now, moving towards next algorithm, that is rate monotonic first fit scheduling, RMFF algorithm. RMFF algorithm improves upon RMNF by using a first fit strategy instead. After sorting tasks by period, it tries to place each task on the first processor where it fits. This seemingly small change leads to better bin packing and thus better processor utilization. Then the first fit decreasing utilization FFDU algorithm. FFDU takes a different approach by prioritizing tasks with higher utilization. Instead of sorting by period, it sorts tasks in decreasing order of utilization before applying the first fit strategy. This prioritization helps in placing the bigger task first, which typically results in better overall packing. Then finally, rate monotonic general task RMGT algorithm. RMGT represents a more sophisticated approach that builds upon the ideas of the previous algorithm. It uses improved feasibility bonds and more complex allocation strategies. RMGT considers not just the utilization of tasks but also their harmonic relationships. Two tasks are considered harmonic if one period is a multiple of the other. RMGT leverages this property to achieve even better processor utilization. Specifically, RMGT can achieve utilization bonds approaching the natural logarithm of 2 times n, which is approximately 69.3% for n processors, which is very close to the theoretical optimum for rate monotonic scheduling. In practice, RMGT often performs even better than this bond suggests. These offline algorithms find applications in various domains, such as automotive systems, where tasks like engine control, brake systems, and climate control must be scheduled efficiently. Then, avionics, where safety critical tasks must be guaranteed to meet their deadlines. And manufacturing systems, where process control tasks need precise timing. In conclusion, while these offline algorithms provide a powerful tool for efficient scheduling, selecting the right algorithm depends on your specific system requirements, including utilization targets, predictability needs, and implementation constraints. Having covered the offline strategies, now let's shift our attention to online algorithms. Online algorithms, which operate in a fundamentally different environment than the offline methods we just discussed, as online algorithms are designed for scenarios where jobs arrive unpredictably and scheduling decision must be made immediately without complete information about future tasks. In real world systems, particularly in dynamic environments like cloud computing or interactive systems, we often can't predict what task will arrive or when. Online algorithms face the fundamental challenge of making good decisions with incomplete information. Methods like next fit M and rate monotonic first fit algorithms make allocation decisions on the fly without knowing what jobs might come next. Talking about next fit M algorithm, the next fit M algorithm is an adaptation of the next fit bean packing approach for online scheduling. When a new task arrives, next fit M attempts to place it on the current processor. If it doesn't fit, it moves to the next processor and tries again. The simplicity of next fit M makes it computationally efficient, which is an important consideration when decisions must be made quickly. However, this simplicity comes to at a cost of potentially suboptimal processor utilization. Then the rate monotonic first fit RMFF algorithm improves upon next fit M by trying each processor in order than rather than simply moving to the next one when a task doesn't fit. When a new task arrives, RMFF attempts to place it on the first processor where it can't where it can be feasibly scheduled according to rate monotonic analysis. This more comprehensive search often leads to better processor utilization. Then, research has shown that online algorithms typically achieve lower utilization bonds than their offline counterparts. While offline algorithms like RMGT can approach utilization bonds of 69.3%, as we discussed earlier, online algorithms often have bonds closer to 50%. This performance gap represents the price of uncertainty and the cost we pay for not knowing the complete task set in advance. So, now let's talk about the real world applications of online algorithms. Online algorithms are essential in numerous real time systems like web servers handling unpredictable request loads, operating system managing user initiated process, then embedded controllers responding to environmental inputs, and cloud computing platforms with dynamic virtual machine allocations. So, in conclusion, while online algorithms may not achieve the theoretical efficiency of offline methods, their ability to make immediate decisions in uncertain environments makes them indispensable for many real time systems. The trade off between immediate decision making and optimal allocation represents a fundamental challenge in dynamic scheduling environments. Let's take a moment now to compare these two approaches side by side. When we compare offline and online approaches, a clear contrast emerges. Offline algorithms typically achieve better processor utilization because they can optimize the entire job set, but they came with a higher computational cost and require complete job information. On the other hand, online algorithms are more nimble and cost effective in dynamic environments, though they might use more processor than necessary. So the choice between these strategies really depends on the system requirements of the system and how predictable our job arrivals are. Next, let's look at the strengths of using approximation algorithms overall. One of the standout strengths of the approximation algorithm is their predictable worst case performance ratio. This means that even in the worst case scenario, we have a clear bond on how many processes will be used compared to the optimal solution. These methods are also highly scalable, which is essential as the number of jobs increases. Most importantly, the feasibility guarantees provided by these algorithms ensure that all deadlines are met. That is an absolute must in real-time systems. Of course, every approach has its trade-off, and so now let's discuss some of the limitations and challenges. While approximation algorithms offer many benefits, there are trade-offs to consider. For instance, offline algorithms, despite their efficiency in processor utilization, require complete knowledge of all jobs and can be computationally heavy. Online algorithms are more lightweight and flexible, but this sometimes results in using more processor than might be strict necessary. Recognizing and balancing these trade-offs is essential when choosing the right algorithm for a given application. Now let's discuss the real-world implication of these findings for multiprocessor systems. These algorithms have significant implications for real-time multiprocessor systems. By ensuring that time-critical jobs are executed reliably, they help guarantee system stability and safety. A key requirement in domains like aerospace, automotive, and industrial control. Ultimately, these approximation methods support the design of robust, dependable control systems that can operate continuously under tough conditions. Now let's look at how these ideas are making an impact in industry. In practical terms, these scheduling algorithms are already being adopted in various industries, particularly in embedded systems and real-time control applications. By optimizing resources, by optimizing resource management and improving energy efficiency, they contribute directly to better system performance and lower operational cost. These improvements not only enhance the reliability of the systems, but also providing tangible economic benefits, making these techniques highly relevant in today's competitive technological landscape. Next, I would like to highlight the contribution of this research. This research has made several important contributions. It establishes clear theoretical performance bonds that let us know how close our approximation are due to optimal solution. Moreover, it bridges the gap between theoretical models and practical implementations, providing a unified framework that accommodates both offline and online scheduling strategies. These contributions are fundamentally in advancing the field of real-time multiprocessor scheduling. While these contributions are significant, there are still challenges ahead. So let's explore some of the open problems and future research directions. Even with these advances, several open problems remain. Future research could focus on tightening the performance bonds even further, making our approximation even closer to optimal. There's also a strong need for adaptive online scheduling techniques that can adjust in real time to changing conditions. Finally, as we see the rise of multi-core and distributed systems, integrating these algorithms into emerging architectures will be an existing and necessary step. These challenges offer great opportunities for further innovation. As we reach the end of this presentation, let's summarize the key findings. Approximation algorithms offer a practical solution to the NP-hard problem of scheduling time-critical jobs on multiprocessor systems. While offline algorithms can achieve superior processor utilization, online algorithms are essentially for dynamic and real-time environments. Overall, the research provides strong theoretical guarantees that translate into practical reliability, ensuring that deadlines are met even in complex systems. In summary, we have seen how approximation algorithms help overcome the challenges of scheduling in multiprocessor systems by offering bounded predictable performance. Their strong theoretical foundation and practical feasibility tests make them indispensable for real-time system design. Thank you so much for your attention. And now I would like to open the floor for any questions.